Okay, so in this video, I would like to continue with subtopic 5.2, which is about induced EMF. So in this subtopic, you need to know about Faraday's and Lenz's law, and you need to know how to calculate for three different cases lah. Induced EMF for three different cases, which is for straight conductor, a coil, and a rotating coil. So first of all, I would like to introduce you with these particular equations. Okay. This one is actually represent induced EMF. Okay, we call this symbol as epsilon, and this is actually represent induced EMF. So like I told you before, the induced EMF, it only happens or occurs when you have a change of flux, right? So yesterday I showed you when I tried to move the magnets and what will happen to the voltmeter. So the voltmeter reading there actually represent the induced EMF, and the change in magnetic flux represented by dphi over dt here. So this part over here is what we call Faraday's law. So basically, Faraday said that the induced EMF is directly proportional to the rate of change of magnetic flux. So I can write down this one as EMF is directly proportional to dphi over dt. Okay, dphi here is change of flux. And if you guys still remember, in previous video, change of flux. Flux here is represented by BA cos theta, right? The phi there represented by BA cos theta. So if any quantities of BA or theta changes, then you will have a change in flux. Then eventually you have induced EMF. Okay, and then one more thing about this equation is that you have a negative sign over here. Okay, this is because according to Lenz's law, says that an induced current always flows in the direction that opposes the change in magnetic flux that causes it. So current always, where to write, induced current always flow in a direction that oppose the change in magnetic flux in that causes it. Okay, we discuss more about the direction, but again I just want to restate. So here it says that epsilon is equal to negative dphi over dt. So most of the time when you try to calculate, you basically focus on this part. Okay, and then this one explain about the direction. So this equation consists of two laws, Faraday and Lenz's law. Faraday's only state about the magnitude of the EMF, induced EMF, and Lenz's law will explain about the direction. Okay, so according to Faraday's law, if there's any change in flux, you will expect to have induced EMF. So how does that happen, and how to determine the direction using Lenz's law? So let's say if you have a flux, we know that flux is equals to BA cos theta, right? So if any of these quantity changes, like if you say the BA or theta, then you expect that phi will change as well. So let's say, okay, let's say if you have an example over here, we have a uniform magnetic field going into the page like that. So let's say I put this one as B. Okay, so this B is the magnetic field that exists over there, and initially it's going into the page. Okay, let's say what will happen if the magnetic field, the magnitude of magnetic field increase. Okay, so it increase. So how does this happen? Okay, maybe you can imagine, let's say if you have a circular loop, like this is my example over here. Let's say the circular loop is like that, right? And it is connected to a galvanometer there. Okay, maybe you have a magnet over here. So the knot is pointing in that direction, the south is pointing in there. So you expect that the field will be pointing in that direction. Right. So that's why if you look from this point of view, you can see that the magnetic field is going into the page like that, and the direction is like this. So when you try to move the magnet closer, so initially it's further away, and if you bring closer, you will expect the magnetic field to increase. Okay, so this is the situation here. So what will happen if there's an increase in magnetic field, then we induce in magnetic field as well. So induced magnetic field, we try to oppose the change according to Lenz's law, right? So try to write down what will happen. So initially magnetic field increase. Okay, so induce B, I put this one as B prime. We try to oppose changes. This one is according to Lenz's law. Changes. Oops. Okay, so initially you have magnetic field going into the page, and then that values increases. So you expect that the maybe numbers of line increases. So to oppose the changes, induced magnetic field will try to produce magnetic field in opposite direction. Okay, so that you have less magnetic field, resultant magnetic field less going into the page, right? It's try to oppose. So this is your B prime or B induced. So if you want to determine the direction of induced current and induced EMF, you have to use right hand grip rule, and you have to refer to this particular direction, the B induced. Okay, so if you are using right hand grip rule, induced magnetic field will produce, I write this one first, induced B produce EMF induced. Okay, using Ohm's law, V equals to IR. So if you have V, which is the induced voltage there, induced EMF, you expect to have induced current as well. So I induce produce. Okay, the direction of I induce, you have to use right hand grip rule. You now can determine the direction of induced current. Okay, so if you want to use the right hand grip rule, you have to follow the direction of induced magnetic field. So the induced magnetic field is going out of the page, so you use your thumb and put your thumb in the same direction of induced magnetic field out of the page. So your hand will curl towards the direction of induced current. So this is your current direction. Okay, and this would be your direction of induced magnetic field there. So here you can see that induced current will be in this direction. Okay, and if you want to focus on the deflection of the galvanometer, if you have a galvanometer that's sitting over there like that, if the current is going in this direction to the right over the galvanometer, so the the point will be deflected to the left, okay, in the opposite direction. So here I can write induced current produced according to Lenz's law. Okay, direction of induced current we try to oppose change in flux. Okay, so this is how you do it, but obviously there's a shortcut to that. So let's say if you have, I repeat again, so if you have a circular loop like that, okay, and then you have your magnets going into to the left like this, so you can straight away use your right hand grip rule. So what you guys need to do is just that you have to point your thumb so that it opposes the direction of the incoming magnets. So there you can see that the knot is pointing to the left, so normally it will be pointing in that direction, right? So what you're gonna do is that you have to point in the opposite direction like that. So over here, that will be your thumb to the right. So you can see that the direction of current will be in this direction. Let's say this is the front side and that one is the behind side. So this is the behind, right? So you can see that for the front side, it will be going downwards, and behind that it will be going upwards. Okay, this is the case when the magnet of knot is going in that direction. What happens if you have, let's say the sound is now going in that direction? Okay, just change the color first. Again, this is the circular loop. Instead of knot, you have sound going in that direction. So if you're following the direction of the magnets, it will be in this direction, right? So to oppose the change, will be in that direction. Okay, so in this case, your thumb is to the left, so your current will be pointing in that direction. Again, this is the behind part. Just put a dotted line there. Okay, maybe you can try to look at a few more examples. But if now you have a magnet of N going away, so let's say this is our circular loop, okay, and the knot is now going out away from the loop. So initially you have your thumb to the left, so the thumb is being, it is being carried away. So initially it is inside the circular loop itself. I just find the diagram there. Okay, so initially it is inside there, so it's being pulled away. So to recover the loss, you have in the same direction over there. Okay, so in this case you will have induced current in that direction. Okay, so the key idea here is that the direction of your induced current will try to oppose the changes. Okay, so this is an example for tutorial question 7b. It says that a circular coil lies flat on a horizontal table. A bar magnet is held above its center with its knot pole pointing down and released. As it approaches the coil, what will happen? So you have a circular coil flat on horizontal table. Okay, so let's say if you have a magnet that now going down, right? If you want to see it from that view, like that. So this is the knot side. Okay, so you have your magnetic field going out on the page, going out from the knot pole. So if the knot pole is pointing towards this particular loop which lies on the table, so you can see that the magnetic field is actually going into the page. Okay, into the page, so it's an X, And remember that this magnet is going into, so I mean it's moved forwards, right? So the magnetic field increases. So to oppose the changes, okay, induced magnetic field will try to produce in opposite direction. So if you use right hand rule, you can put your hand like this. So your thumb now pointing out of the page, okay, which is pointing opposite of the knot, right? And because of this, the induced current will be according to the curl there in that direction. So induced current anti-clockwise direction. Okay, so the easiest way to to really understand the direction, okay, the way I understand this is that your thumb will be pointing towards north, right? Okay, and your behind here pointing towards south. Okay, so if you have a magnet like this that is going in that direction to oppose, so you have to put knot against knot. Okay, like this one you have a south, so basically you want to oppose, you have to put the south over here, so your knot is over there. So this is the induced magnetic field. So south and south try to oppose. Okay, like this one, if you want to pull away, so basically you want to hold back the magnets inside the circular loop, so you have to put the opposite direction over here. So instead of knot, you put knot and south over here, so they will try to pull back. So that's the idea lah. So in this case, if you do it like this, then I think it's much simpler. Okay, last example, I'll just show you one more time. Again, this is the circular loop. Now you have a south that is going away. So if you want to use your right hand rule, basically you want to pull back the south there. So the south is going away. If you want to pull back, you want to put a magnet that north is over there and south is over there. Okay, so basically your thumb will be pointing to the right and your behind there to the left. Huh? So here in this case, where's the diagram? Will look something like this. Okay, your thumb following the north direction and your S south will be in that direction. So induced current will follow the curl, so you will have in that direction, will be in that direction. Okay.